All right, good afternoon, chemists. We'll get started now. Left off on chapter 2. Chapter 2 is a relatively short chapter. They finally fixed my microphone. I feel like me again. We'll finish chapter 2 here. It's relatively short. We did calculations last class, and that went rather quick. But to look forward to, ending chapter 2, we move on to chapter 3, which is chemical reactions, and we'll do some chemical reactions if we make it to chapter 3. So let's get started. Actually, before we get started, I just wanted to make a quick announcement about the tutoring resources that we have here in the chemistry department. So I mentioned this before on the first day of classes, but we have 2 different drop-in tutoring centers, free, absolutely free. All right, for you to utilize. One of them is in the first floor of Celeste. It's, how you walked in and you went to the right to get your lab coat? Well, you go to the left to go to the Learning Resource Center, where there's always 2 or 3 teaching assistants there to help with any lecture content questions, midterm questions. If they say, oh, I'm a 1210 TA, just don't listen to them. Chemistry is chemistry. It doesn't matter. All right, the stoichiometry we learn in this class is the same stoich that they learn in 1210, so just don't listen to them if you want extra help there. But I think what might be more useful for you guys is the second floor of Celeste also has a lab tutor space. It's the second floor of Celeste. I know our labs are on the 3rd floor, so you have to go to the 2nd floor. But it's in that middle space. It's really nice. There's always a TA or 2 there that can help with lab-specific questions. You all, in fact, do the exact same labs 1210 and 1220 does. So any one of those teaching assistants can help you with technical problems, pre-labs, post-labs, any of that. They should help. Right, so there's that information. They're open Monday through Friday, like during normal business hours, like 9 to 5 or something like that. It might be on that QR code. I'm not sure. All right, so, all right, let's go back to chapter 2, where we are talking about atoms, elements, and we're thinking about the usefulness of the periodic table. So I showed the different parts of the periodic table, what you will be responsible for. So the parts, we have groups versus periods. Our groups are the columns. The rows are our periods. The different parts to understand is oftentimes I'll refer to main group elements. Main group elements includes groups 1A through 8A. So I'll just highlight them here, all right? So groups 1A and 2A are part of the main group. You would think 3A is next, but it's not. 3A starts actually over here. I actually don't want to highlight it that color. I'll do it pink, this color, all right? So those are main groups. This group is a part of the main group, so 3A, 4A, 5A, 6A, 7A, 8A, all of those columns. So kind of the left and right outermost columns, not the middle part. Those middle elements I have labeled in red. Those are our transition metals. They have different properties due to different electron configurations that they have. All right, so referring to the main group elements versus transition metals. More important, from the periodic table, we can determine what kind of metallic character certain elements have in their pure form. So how I like to interpret the periodic table is I understand that on the right side of the periodic table we have nonmetals. On the left side we have our metals. In between those we have things that are not quite metals, not quite nonmetals. We call those metalloids. And so I reference myself. I know where the metalloids are. They are right here. They're the yellow ones along this stair-step region. I've highlighted them, where we have boron, silicon, germanium, and then it kind of does this stair-step business here. All right, and so what's nice about, if you know where the metalloids are, anything to the left of that is a metal. So even the transition metals, yes, they're metals, along with these main group metals. And then we have our non-metals on the other side of it. All right, so that's a good way to reference yourself there. All right, and we do know, even though hydrogen lives with the metals, is it a metal? It is not a metal, it's actually a non-metal, okay, even though it lives over there. Okay, so let's put it all to use and see if we can't do some reading comprehension and utilize what was on the previous slide, but no worries. If you want to answer this question, do refer back to the previous slide, but these are common like exam questions, okay? Name a halogen in period 5. Period means what? Row. So that's kind of what we need to comprehend here. Halogen implies what? It implies a column, but which one? 7A. Yeah, so this is it's kind of like, what's that game? Battleship, right? So we got our row, we got our column, so now we just have to find our target here on our periodic table. So row 5, we can start at hydrogen 1, 2, 3, 4, 5. So it's one of these elements, okay? And so we are looking at group 7A, so it looks like this is iodine. All right, next, let's name an alkali metal in period 3. So row 3 we are looking at now, all right? But alkali metal implies what group? That's the common name. This is 1A. An alkali metal is the 1A, so the first column. So what element is this? Sodium, yeah, so this is Na, so sodium has one of the weird element symbols. Sodium, yes, there's not an N in sodium, right? There's not even an A in sodium, no. So sodium does have that symbol Na, so it's sodium, yes. Yeah, so many of these symbols come from Latin or other languages, yeah. I'm not very good at languages, including English, and even though it's my only one. So I can't comment on the origins of names, but I should know more. A lot of my friends are chemists, believe it or not, and a lot of them like to name their children, their like offspring after elements, which I think is weird, in my opinion. Okay, let's keep going. I name my cats after Greek gods, so maybe it's not as weird. I don't know. All right, let's name an alkali earth metal in period 4. What's alkaline earth metal? 2A, yes, yes. So this is what element? Just tell me. Calcium, perfect, okay. Name a noble gas in period 2. Noble gas means 8A, and so this is element neon. All right, so now we're gonna get a little bit different. Let's name a 2 5A metalloid. So I'm just straight up telling you 5A. So one of these elements here, all right, in 5A. But which ones are metalloids? Yeah, so it's the ones that are touching the staircase. So it's arsenic and SB, my favorite element. It's antimony, yeah, I know, SB, there's like literally no common letters. I should look up what the the language significance is there, but antimony is my favorite. So we have arsenic and antimony SB. I like it because no letters match at all. Okay, name a 4A nonmetal. So same idea, we're gonna go to 4A, but where are our nonmetals at? Are they going to be under the staircase, above the staircase, on the staircase? It's going to be above. So which one is it? Carbon, yes, perfect. And so there's only one, so in this case, carbon. All right, so those are the kind of questions to expect on the exam about navigating the periodic table, okay? And how we can make it, I can make it a little bit harder is, I'm not going to ask you to actually spell something out, right, to like type it in. But I could say something like, how many protons does antimony have? But I could spell it out. But you need to know antimony is element SB, all right? Because our periodic tables I give you on exams don't have element names. They have element symbols, masses, atomic masses, and all of that. Just no actual names on them, all right? So you do need to know antimony is SB. Silicon is Si, element 14, but selenium is 34, right? So we do need to know those differences. Okay, so let's move on to naming. And so the big idea with naming here is we have two categories. And it has to kind of do with the periodic table. We have metals and nonmetals. So there's two types of categories we will look at here, and that's ionic salts, name those, and molecular compounds, name those. And so the first step to that is, can you identify it as an ionic compound or molecular compound? And it has to do with what elements are present, all right? Ionic compounds contain ions. Who'd think that? Yes. Ionic compounds contain ions, where we have positively charged particles, negatively charged particles, and they're attracted to one another in this crystalline network. And so when you have an atom or an element that is in its ionized stage, or an ionized state, the number of protons and electrons do not match. So we can calculate the charge of a single particle by comparing protons to electrons. For the most part, when we were doing like isotopes and stuff, we were looking at charged neutral atoms, so protons and electrons were equal, but now we're gonna start talking about, okay, charged things have unequal protons and electrons. Okay, so anions, so just for conventions, anions are negatively charged, cations are positively charged. All right, both of them are ions. So if I'm just referring to, like ions in solution, referring to both positive and negatively charged things, I will call them ions. But if I'm just referring to a sodium ion, which is positively charged, it's more appropriately called a cation, a cation. So how I remember the charges is that a positive sign looks like a T, and cation has a T in it. And that's how I remember the charges. I don't have one for anions. So I just remember cations are positively charged and anions are the other one. All right, so that's just to be very specific with our language, and I will try to follow that, but you can generally refer to anything that's charged as an ion, but we can be hyper-specific and say cation or anion. And so what you see here is that anions are typically nonmetals on our periodic table, so the right part of our periodic table. Right, those elements tend to form negatively charged things, while our metals on the left side of the periodic table, they tend to form cations. They tend to lose electrons. And we'll learn why here soon enough. So just for now, it's something that you should just memorize, that cations come from metals, anions come from nonmetals. So to form an ionic compound, if we combine a metal and a nonmetal, we typically form something that's ionic. That's what you want to look for ionic compounds. Okay, so how do we predict charges for ionic things? So ions, they have to have a charge. Electrons, that's something you can count. Like you can lose one electron or gain one electron. You can't lose a fraction of an electron. So elements on the periodic table, based upon where they are, we can predict a lot of their properties, such as charges. And so here are the rules. This is specific for main group elements. So remember what our main group elements are? They're the ones that aren't the middle transition metals. They're the ones on the left and right. All right? It's real easy. For a cation, anything that's a cation and it's a main group element, its charge is its group number. It's really nice, right? So a sodium ion has what charge? Just look at its group. It's in group 1, so it is a +1 ion. As an ion, sodium as an ion will be a +1 charge, right? Versus calcium. Calcium as an ion will adopt what charge? Don't look at that one, just look at the periodic table. Look at the periodic table. It's going to have a charge of 2 because it's in group 2A, yes. And that's it. Aluminum. Aluminum's going to have what charge as an ion? +3. Is that something we need to memorize? I don't count it as memorizing because it all comes from the periodic table, all right? Everything in group 1, lithium, sodium, potassium, as an ion is +1. Calcium, strontium, barium, all +2. Aluminum, +3, all right? Those are for our metals. And so the great thing about naming metals, metal ions, is the name of the ion is just the element name. So if I'm talking about a calcium 2+ cation, not the atom, I just call it calcium ion. That's it. That's it. Things get a little different for anions. Things that are negatively charged, they gain electrons, all right, and that's how they form their negative charge. And so we are looking at mostly non-metals here, all right? Cations, these are metals. The anions, these are non-metals, right? So the charge of an anion in our main group elements, it's the group number -8, all right? So all of group 7A anions form -1 anion charges. All group 6A, oxygen, sulfur, selenium, all form 2- anions. So that's the trend there. It's group number -8. But the names of anions is a little bit different than cations. Cations, it's just the name, the metal name. But for anions, we take the element name, we drop the ending and add "ide" instead when talking about the ion form. So if I'm talking about an oxygen atom or an oxygen molecule, I just say oxygen. But if I'm referring to oxygen 2-, I don't call it oxygen, I call it oxide ion, all right? Or let's do another one. So oxide, chlorine, right? I can talk about a neutral chlorine atom, but Cl-, the anion, is called what? Chloride. What about bromine? Bromide ion as an anion. What about nitrogen? Nitride, yep, that's it. What about hydrogen? What if I have a H-? What do you think? Hydride, yep, that's it, okay? So anions, when they're an ion, have the "ide" ending. If we're talking about the neutral thing, then we use the normal element name, like chlorine, oxygen, all that. Okay, and those are nonmetals. Okay, so what about all of the weird transition metals in the middle? Okay, they're called transition metals because they are hard to predict. All right, that the electrons in these transition metals harder to predict, so we can't do what we did in the previous slide and just say, oh, like all group 1s are +1, all group 2s are +2. Transition metals, I have to tell you what the charge is. I have to tell you, right? So I love transition metals because it uses what's called the stock system, where we have to use Roman numerals to tell you exactly what the charge is. So it's even easier than memorizing because I'm telling you the charge, right? So for example, iron, Roman numeral 3. What ion do you think that is? It's an iron with what charge? +3. I love the stock system because it literally just tells you. Copper 1. What is that? Copper with a +1 charge. Perfect. All right. Let's go the other way. What if I'm working with a cobalt 2+ cation? What should I call that? Cobalt, Roman numeral 2, and that's it. Ion, and then this SN. What element's that? That is tin. That is tin. So this is tin 4. Oh, I skipped some, didn't I? All right, and so this is super important. So I skipped over this one on this. I zoomed in too far. We have copper 1, all right? So that implies copper just with a +1 charge. With this, copper 2. Is this copper different? Yeah, it is. Where this copper is actually copper 2+ cation. So we got to be super careful with transition metals and how we communicate these ionic compounds, because copper 1 and copper 2 are completely different substances. I can't just say copper oxide. If I just say copper oxide, I don't know what the charge of that copper could be, because copper exists as +1 or +2. So we have to be hyper specific and say copper 2 oxide, right, to be more specific. Rust. A lot of people just call it iron oxide, but that's actually a little too generic because there's multiple oxidation states of iron. So iron oxide as rust should better be named as iron 3 oxide is the full correct name for rust. All right, and this last one, what is this? This is gold, Roman numeral 3. I love the stock system because it just tells you the charge. Okay. All right, so those were predicting charges, stock system. So unfortunately, these polyatomics, you just need to memorize. So polyatomic ions are an entire unit of atoms that are bonded together, that the whole thing is charged. All right, so these polyatomic ions, they don't break apart at all when they are involved in chemical reactions. We'll look at these in double displacement reactions. They kind of move as a completely charged unit. The whole thing, the whole group is charged. All right, so we said that chlorides are negatively charged. Well, hydroxide, this OH group, is also negatively charged. Nitrate, a nitrogen attached to 3 oxygen, that whole thing is negatively charged. Just like chloride, bromide, iodide, those are all negatively charged too. So you can kind of think of replacing, any one of our anions with a polyatomic instead. They're just a little bit more complex. So what you need to know here are the formulas, obviously, the charge, and the name. Right? But there's some tricks here. There's some tricks to this, especially for these oxyanions where we have these oxygens attached to them. All right, so like we have nitrate, but then there's also nitrite, but they're related to one another by an oxygen. We can have sulfate, but also have sulfite. We can have chlorate, we can have chlorite, we can have perchlorate, and we can have hypochlorite, and it all has to do with oxygens. And so here's the trick, right? An oxyanion is something with a nonmetal and an oxygen attached to it. So, for example, sulfate, phosphate, permanganate, chlorate, all of those are a nonmetal, okay, not permanganate, sorry, a nonmetal with oxygen attached to it. So if we just adjust the number of oxygens, the name, prefixes, and suffixes just change a little bit. So, for example, here we have nitrate. If we remove an oxygen, so here we have nitrate, that's one you just need to remember. This is nitrate ion. If you remove an oxygen, you change the 8. If there's one less oxygen, change the 8 ending to ite. So if NO3 minus is nitrate, NO2 minus is what? Nitrite. That's it. That's it. So in my mind, I memorize these rules, and I memorize all of the 8 ending ones because I can always just adjust it from there. I reference myself to the 8 ending. All right, so I'm going to tell you SO4 2 minus, this is sulfate. Sulfate. So what do you think SO3 2 minus is? Sulfite, yes. Okay, so we're doing good on the subtract an oxygen. Note how the charges aren't changing. So we're changing the oxygen, we're changing the name, but the charges don't change. Thank goodness. Okay, so let's do a harder one. Let's do the chlorines. All right, so I'm just going to tell you that ClO3 minus, this is called chlorate. So let's just do the one that we've already done a billion times. What's ClO2 minus? Chlorite, okay, chlorite. Yeah, so there we did. We removed an oxygen, and so we call that chlorite ion. 1 oxygen. What if we remove an additional oxygen? So that's what we have up next. If there's 2 less oxygens than normal, you're going to have the ite ending, and then you're going to add an additional hypo prefix. So I like to think, okay, chlorate, remove an oxygen, it becomes chlorite. Remove another oxygen, add a hypo to it, but keep the ite ending. So ClO minus, this is called hypochlorite. Hypochlorite ion. All right, that's what bleach is. Sodium hypochlorite is bleach. Right? Okay, so that's removing oxygens. It goes ite and then hypo. Now, if you go back to the normal 8 ending and add an oxygen, the rule is you add a per prefix, but keep the 8 ending. So that's what this first one is, going from 3 oxygens to 4 oxygens. This is called perchlorate. Perchlorate. All right? Those are the rules. So that means if this, BrO3 minus, if this is bromate, what is the formula for hypobromite? If that's bromate, BrO3 minus, what is hypobromite? BrO, how many oxygens? Just one, and the charge is overall 1. All right, perfect. Okay, so let's keep going. So those are our polyatomics. You just need to memorize them. I'm sorry. Use them, and then it won't be as bad. So let's write some ionic compounds. We studied cations, anions. Now let's combine them so it makes a neutral ionic compound. Because when we write ionic compounds, NaCl, salt, they need to be charge neutral, right? Because it represents the ratio of cations and anions that exist in this crystal lattice. So the idea here is we just need to combine these ions in such a way where the charges balance with one another, so we change the subscripts on these. So for example, if I combine a magnesium and a fluoride, I ask myself, how many of each of those do I need? How many positive things, how many negative things of each do I need to make it charged balanced? So for every 1 magnesium, that's 2+, how many fluorides do I need to balance that charge? I need actually 2 of them. All right, so I'm going to call this compound MgF2. So at this point, this ionic compound, I have the correct ratio of cations and anions, but note how I've now gotten rid of the positives and negatives in the superscripts. Because I should always know that magnesium is a 2+ cation. I always know that fluoride is a -1 anion. So there's no use. I don't need to rewrite those charges in the corner as long as I have the correct ratio that's there. All right, so we don't have to rewrite these positives and negatives there. All right, so 1 cation for every 2 anions to make that charged balance. I guess I can show you, I like to think of it like this way. I think, okay, that's +2. Let's bring a minus in there. Oh, if I add another minus in there, now it all equals 0. Some people do like the superscript, subscript swap. Some people do that too. I have it up there if that works for your brain as well. All right, so, but I just like to think of what's the cation-anion ratio to make it charge balance. All right, so barium and carbonate. What's the ion ratio I need? Yeah, it's just going to be 1:1. Perfect, all right? So if it's 1:1, I can just go ahead and write BaCO3. All right? Barium is always a 2+ cation. So from this formula, I can always tell that carbonate is a 2- anion. All right, next one, ammonium phosphate. So how many of each do I need? How many ammoniums do I need? I need how many ammoniums? 3, and then how many phosphates? 1. So be careful here when ammonium is a polyatomic. So I need 3 of them. So when I write ammonium, NH4, I want to put that whole thing in brackets and put a 3 because I'm denoting, hey, I want 3 of these groupings of atoms. Right? And then you can just tack the phosphate on the end. Since there's just 1 phosphate, I don't need to put that in brackets as well. Unless I had if I needed 2 phosphates, then I would. All right, and then finally, aluminum oxide. So here, maybe doing the swap would be useful here. Recognize if I have 3 oxides to give an overall -6 charge, I need 2 aluminums to give an overall +6 charge, so then it cancels out. So this compound is Al2O3. All right? Okay, so all of these charges on this slide, you should know. These are things that either can come from the periodic table to be memorized or the few polyatomics to memorize, right? Including phosphate and ammonium and carbonate. Those are common ones. Okay. All right, so now let's finally name ionic compounds. So again, the important thing to name an ionic compound is you need to first identify it as an ionic compound. If it's not an ionic compound, it's not going to work, the naming convention. So what you want to look for, usually, is a formula that has a metal and a nonmetal in it. That's what you want to look for. Because metals tend to form what kind of ion? Cations. Nonmetals tend to form anions. So if you have a cation and anion, you're going to have an ionic compound. Or, all right? It doesn't always have to be a metal and a nonmetal. It can also just be ions. If you have multiple polyatomics present, like positively and negatively charged ones, that too can be named using ionic rules. Ionic compounds just contain ions. Most of them are metals and nonmetals. So the basic rule for naming ionic compounds is you just name the cation, then you name the anion. That's it. You never, ever, ever tell the reader how many of each ion there are, ever. And I only point that out because the rule is different for molecular compounds, right? Carbon monoxide, carbon dioxide. You know how we use those prefixes to mean like 1 and 2 and 3? Carbon trioxide, if that exists or something. We never do that for ionic compounds. You never have to say magnesium dichloride. That is wrong. You only ever say magnesium chloride. Here, what ion is this? What metal is that? Potassium. Then what's the name of that anion? It's not sulfur, it's sulfide. So all this is potassium sulfide. That's it. You never, ever, ever have to say how many of each ion there is. You just have to name them. The reason you don't have to say how many there are is because we can always predict the charge of ions. So from the name, we can get the cation-anion ratio because we know what the charges are. So let's just go through these. All right, this one's magnesium chloride. This one is potassium sulfate. Oh, sorry, not sulfate, sorry, sulfide, sorry. Sulfur, sulfide. I always remember chlorine, chloride. So then if it's sulfur, then it's sulfide. All right, next one, what is this one? Yes, we'd think it's iron oxide. Yes, so you were great in that you just named the metal and the nonmetal, but we have a problem here. I said that we never have to denote how many of each there are because we can always predict the charge. That's true for magnesium and chlorine because they're main group elements. That's true for potassium and sulfur because they're main group elements. Is iron a main group element? Nope, it's a transition metal, so we need to use what? We need to use Roman numerals, all right, to be absolutely correct, okay? And so the Roman numeral indicates the charge of the iron atom or the iron ion. Can we figure out what the charge of the iron is? Yeah, if we kind of deduce it. Because do we know what the charge of the oxygen is? Yes, we do. Oxygen is a -2 anion, but how many are there? There's 3, so there's a total of -6 coming from anions. So can you tell me what the charge of iron is? It's +3. It's +3. Because there's 2 irons. There's 2 irons. Each of them contributes 3 to give a +6. Cancel that out. All right? So this whole name is iron 3 oxide. All right, next one. What is that? Ammonium. Ammonium. And then what's the second thing? Sulfate. Here's an example. Is there any metals in that? In ammonium sulfate, are there any metals? Nope, no metals. Just all? No. So that's kind of weird because I just told you that, you know, ionic compounds usually it's a metal and a nonmetal. But this is an example where it's not. It's actually all nonmetals, but that's absolutely okay because ammonium sulfate, it still contains ions. So that's why it's an ionic compound, right? Because it contains ions. Ammonium is an ion, sulfate is an ion. All right, next one. What is this? Chromium nitrate. So nitrate is one of our polyatomics that you memorize. But is this completely right? No, what's wrong with chromium? It's not a main group. It's a transition metal, so you have to tell the stupid reader what the charge is because they can't predict it using the periodic table. So what is the charge on chromium have to be? 3, because each nitrate is 1. All right? If you can't predict it on the periodic table, you have to tell the reader what charge it is. All right, and then the last one, this one's tricky. Well, the first one is sodium, but we need to figure out what that is. So ClO minus, what is that? It's one of the chlorate ones, right? It's one of the chlorate ones. So I like to just reference myself and think, okay, chlorate is ClO 3. This is chlorate. So minus 2 oxygens, 8 becomes ite, but then we also add a hypo. Yeah, so it's hypochlorite. So this is sodium hypochlorite. That is bleach. Okay. All right, so that's how we name. So let's go the other way. This one's, I think, harder. Maybe, I don't know. So here's our strategy. Well, the question says, which compound possesses the most oxygen atoms? So that means what? We got to write out the formula, and we need to make sure that formula is balanced. So that's the tricky part here, but from the names. So let's do it backwards. We are given the name. I like to identify what is the full formula in charge of the cation, what is the full formula in charge of the anion, and I make sure that everything's charge balanced when I bring in the subscripts. So, sodium, what is that cation? Na what? Plus, because it's a group 1A. Sulfate is one of our polyatomics. That is SO4, 2 minus. All right, so that's just one, again, you need to memorize, and I mean memorized yesterday, because I told you to memorize it on Tuesday. Yeah. And so here we have the ion charges, so now we just have to combine them in a way that they're charged balanced. So the full balanced chemical formula will be Na, 2 of them, with 1 sulfate. Do you agree? Yes. All right, so let's keep going. Ammonium phosphate. Identify what ammonium is. Is ammonium on the periodic table? Nope. It is one of the polyatomics. Oh, wait, that says aluminum. Sorry. I thought it said ammonium. All right. Aluminum is on the periodic table. What is it? Al, what charge? 3 plus. And then phosphate is what charge? Or sorry, I guess I should write it. PO4, 3 minus. Just look at the previous slide. Yes. You won't learn it if you don't practice it and refer to it. All right, and so we just combine those ions. It's a 1-to-1 ratio, so it's just Al, PO4, that's it. 1-to-1. Okay, chromium 3 oxide. I love the stock system. Why? Because what's the charge of this? 3. We don't even have to think about it. It just tells us. But oxide, we do need to know. What is that? 2 minus, yes. And so we swap them. And so this is Cr, 2 of them, O3. Whew. Okay, so calcium carbonate. Calcium has what charge as a cation? +2. And then carbonate is one of our polyatomics. I'm just going to tell you it. It is CO3, 2 minus. So we combine it. This is an example of just a 1-to-1. So this is just CaCO3, that's it. Man, so we have 4 oxygens, 3. Hopefully we hit a big number here soon. Okay, magnesium. Magnesium is Mg, but what charge? +2. Are these things to memorize? No, it just comes from the periodic table. You just have to avert your eyes and see, oh, Mg is group 2, so it's 2 plus. Perchlorate. ClO4, yeah, so I hope you recognize, oh, this is in the chlorate family. So that's ClO3 minus, but with 1 additional oxygen gives you the per prefix. So this is ClO4 minus. So how many cations, how many anions do I need in my balanced formula? Mg, and then how many chlorates? 2 of them. That looks like a big one. That's 8 oxygens there. And then the last one, copper 2 nitrate. What's the charge of copper? +2. And then nitrate is NO3 minus. And so we'll need 2 anions here to make it charge balanced. So this is CuNO3, 2 of them. And so that took a long time to just circle one answer. Which one has the most oxygens in its formula? The magnesium one, yeah. But see how that was a lot harder to do because you had to not only identify the ions, but swap them in such a way where everything was charge balanced. So that means correctly identifying the charges of things. Okay, so we just looked at naming ionic compounds, metals and nonmetals. Okay, so on our periodic table, we got our metals, nonmetals. And it kind of, the periodic table in itself, the metalloids kind of separate these two domains of chemistry. Inorganic chemistry, the chemistry of the non-living, utilizes metals, versus organic chemistry, the chemistry of the living, nonmetals. So we are carbon-based beings. We're mostly carbon, nitrogen, oxygen, all right? We're composed of nonmetals. So the chemistry along, inorganic, ionic compounds, much different than non-metal chemistry, organic chemistry. It's so different that it's two different course sequences. All right, so you're just taking Gen Chem with me, and that's more of an inorganic course, kind of. Versus if you decide to, expand on your chemistry, there's another branch of the living looking at organic chemistry. So you're looking at carbon, hydrogen, oxygen, those types of things. And so big division, big differences in chemistry. Me personally, I like the land of the non-living, right? And so that's what I studied in graduate school. The reason I studied metals is because they're pretty to look at, right? Look at these different oxidation states of vanadium. Vanadium's a metal, so just by changing the charge, we get these beautiful different colors, right? Here's an iron complex. What does that look like? Looks like a violent blood color, yeah? So this is an iron complex. Again, iron, a metal, really cool colors. Versus, most organic chemistry, the synthesis they do, they're working with white powders. They don't absorb light like metals tend to do. But there is a bridge between organic and inorganic chemistry. These aren't just like two separate branches that never interact. No, there's even another branch of chemistry called organometallic chemistry, which combines organic and metals. But let's think of this. I showed you this picture, and we say it looks like blood, but think about what is blood made out of? Hemoglobin, and what's in the center of a hemoglobin? An iron, right? And so there's this cool overlap of inorganic, organic chemistry where we see similar properties come out. Obviously, we're not going to be pumping this complex into your bloodstream via an IV drip, okay? But at least in terms of color, there's cool similarities there. All right, and so the big idea here: inorganic chemistry, organic chemistry. Organic chemistry, all nonmetals. We're going to be looking at molecules that fit under organic chemistry. The inorganic chemistry will contain metals, like metals and nonmetals for our ionic things that we just named. Okay, so like I said, we study it differently, organic versus inorganic chemistry. We name them differently, inorganic ionic compounds versus molecular compounds. And to kind of highlight why there's all these differences is because their structure is different. Right? Inorganic or ionic compounds, you have ions present. So they pack together in this extended lattice where you minimize repulsions between like anions close together or cations close together, but you maximize attractions between cations and anions. Right? So you pack in such a way to maximize those attractions, minimize repulsions. So this is the structure of an ionic compound. So when you have a metal and a nonmetal, when you have cations and anions, they form this structure, a crystalline structure. Versus molecular compounds, these are all nonmetals. They form covalent bonds to one another. They form discrete molecules. You can pick one up. Versus salt, you can't pick up 1 unit of NaCl, because it exists as this extended lattice. But you can pick up a single molecule of water. Water would be an example of a molecule. So we'll explore bonding in molecular compounds more in chapter 7, but the big idea here is what I want you to get at here is the difference in structure of ionic things versus molecular things and how to identify them. To identify an ionic compound, it's a metal and a nonmetal, or anions, or ions, versus molecular compounds are all nonmetals. That's what you want to look for. Okay. So, all right, so let's look at a little bit more and expand now on molecular compounds. Okay, so molecular compounds, all nonmetals. So we're making a shift. We're moving away from ionic things predicting charges. Now we are looking at molecules. Molecules are all nonmetals, nonmetals. All right, so in order to express what atoms are present in a molecule, there's a couple ways we can do that. We can use a molecular formula. So for example, I can just write H2O. H2O has 2 hydrogens and oxygen. They're all nonmetals. I can use a chemical structure, like a Lewis structure, to talk about connectivity. I can say, oh, okay, 2 hydrogens are attached to an oxygen. Right? It's not like in a weird ring or anything. Okay? So both of these are communicating similar things in that I'm talking about water, but to different degrees of specifics. Here in the formula, I just tell you what atoms are present, but here I give you a little bit more, the structure, how the atoms are actually connected. Okay, so here are some more complex structures. So one of the learning objectives of this chapter is, can I give you a structure and you tell me what the formula is? All right, the molecular formula. So we just have to be very careful of counting atoms here. So let's calculate the molecular formula using the chemical structure of this glucose. So we just got to be careful. How many carbons, how many hydrogens, how many oxygens? So I heard it. 1, 2, 3, 4, 5, 6. There's 6 carbons. Let's do oxygens next. 1, let's do a different color. 1, 2, 3, 4, 5, 6. 6 oxygens. How many hydrogens? 12. Yes, very good. 12. So we can write this formula as C6H12O6. Right? All right, let's do the same thing to acetic acid. This one's a little easier. How many carbons? 1, 2. Yeah, 1, 2. 2. How many hydrogens? 4, and then 2 oxygens. Be careful of that hydrogen tacked on the end right there. Don't forget him. All right? So these are the molecular formulas, both that we just determined. We took the full molecule, the structure, just counted up the atoms of each, the elements present. Those are the molecular formulas. They represent of the atoms that are there. We can also represent substances in terms of their empirical formulas. An empirical formula is the simplest ratio of the atoms. So if we look at glucose, C6H12O6, is there a common, what's the word where they all divide by 6? What's that math word? Common. You know what I'm talking about though, right? All the numbers are divisible by 6. Factor, largest common factor, that's what it is, right? Greatest common factor. No, least common multiple is not it. Greatest common factor, it's 6. You can divide 6, 12, and 6 all by the number 6. All right, so that's what I'm trying to get at. All right, all of them are divisible by 6. That's the greatest common factor, okay? And so when we divide all those numbers by 6, we get the simplest atom ratio, CH2O, okay? This is not a molecular formula, it's an empirical formula, right? The word empirical means by experiment. And so when chemists did experiments to try to figure out what the formulas of these things were, all they could get was an empirical formula. They could never actually get a molecular formula without other experiments. We'll come back to this idea a little bit later in chapter 3, so we'll just hold it there. All right, so what is the greatest common factor in acetic acid? What number? 2. So we're going to divide by 2. Anything special here? Interesting. So this atom ratio, empirical, has the exact same empirical formula as glucose. Interesting. So what that means, if we were a chemist in the 1800s trying to separate or distinguish glucose and acetic acid, just using experiments with percent mass, we wouldn't be able to do it, because all we would know is their empirical formulas and not their true molecular formulas. So we'll come back to this idea in chapter 3, so just keep that on the back burner. All right, so let's name molecular compounds. All right, these are all nonmetals, so you need to identify it that way, okay? So how we name molecular compounds is, yes, now we finally just say the prefix of the elements that are there. All right, so here are the prefixes, so do memorize these. I will point out that for these molecular compounds, don't use these rules if there's an H present, because that's an acid. Acid naming rules are different, and it's coming up here, right? So simply, I feel like most people know what this is. What is that? Carbon dioxide. Yeah, so CO2 is carbon dioxide. So yes, I am using prefixes now. Then what is this? Carbon monoxide. Yes. So see how if I just called this carbon oxide, you wouldn't know how many carbons, how many oxygens are there. So you could mix up CO2 versus just CO. So when talking about molecular compounds, we do have to tell the reader how many of each atom are there, because there are no charges to predict, to like figure out and make everything charge balance. Molecules don't have charges like ionic compounds do. So we have to tell the stupid reader how many of each atom there is. All right? So carbon dioxide is different than carbon monoxide because of those prefixes. But note here that when there's one of the first element, you don't have to say mono. It's redundant. But if you do have something like N2O4, you do want to say dinitrogen tetraoxide. Okay. All right, so let's look at some more. So here are the rules again. Prefix, add say the first element, and then the second element that's there, you say the prefix, and then you say the element, but it has to have the "ide" ending, right? Only the second element gets the "ide." All right, so let's go through these. What's SF6? Sulfur, hexa, fluorine, fluoride. If you don't know how to spell fluorine, I just remember that it's not flour. It's like flour is like F-L-O-U-R, but fluorine's the other way. Okay, PBr4, phosphorus, tribromide. Yep, so we're using those prefixes to tell the reader how many of each atom there is. N2O. What is it? Yeah, in this case, we do say dinitrogen monoxide. All right. Like we had carbon monoxide. Here we have two of the first elements, so it's dinitrogen monoxide. All right, SiO2. Silicon dioxide. And the last one is carbon tetrachloride. Perfect. All right, and so what all these elements have in common, all nonmetals. Yeah, all nonmetals. Silicon's a metalloid, but here it's going to have nonmetal characters. Okay. All right, so those are molecular compounds. Let's put it all together. All right. So I'm giving you a hint here. Which picture is molecular and which one is ionic? So what is this picture? Ionic. And then the second picture? Molecular. Okay, great. So following up on that, which substance of this pair is going to adopt structure 1? CO or LiCl? Yeah, lithium chloride, because it's the ionic thing. It's the thing that uses ionic naming rules. Okay, and then what's going to adopt number 2? CO. All right, and so how I could ask this on an exam is I could just give you a name or give you a formula, and I would give you a bunch of pictures, and you would choose which picture that compound looks like, where there's two kind of overlapping ideas. Can you get the atom ratio right? Can you get the cation-anion ratio right? But secondly, can you identify it as a crystalline ionic lattice versus a full-blown molecule? Over here we have discrete things, because there is a difference. Note here how the atom ratio is the same. It's a 1-to-1, but completely different structures. This is ionic, this is molecular. Naming these two, different. One's ionic, one's molecular. So it's not enough that you just know how to name, but I want you to also understand the significance of the structure. Okay, 3 more slides, or 4 more slides. Okay, let's name acids now. Okay, so acids will look like nonmetals, or sorry, look like molecular compounds, but the difference is that there's a hydrogen first. Okay, so like HCl, HBr. Yes, all nonmetals, but H is first, so it makes it an acid. The H plus makes it an acid. So there's 2 types of acids, binary acids and oxyacids, or oxoacids. Binary acids are an H plus that's attached to just a regular anion. Okay, HCl, HBr, HI. Those are binary acids. So to name one of these, you you take the anion. So in this case it's chloride, right? Because HCl is composed of H plus and Cl minus. So that's chloride. You're going to add a hydro prefix, but an ic acid suffix. So this becomes hydrochloric acid. All right, so then versus HBr, Br is bromide. So what would the name of HBr be? Hydrobromic acid. Okay. What about HI? What do you think HI, what that name is? I is iodide, so it would be hydroiodic acid. That's it, right? So this is how I remember it. HCl, HBr, HI, those are all very, very short acids, right? It's just like 2 letters, but they have really long names, and that's how I remember it. HCl, hydrochloric acid. It's a short acid formula, but it has a really long name. And that's different from oxoacids, because these oxoacids have a bunch of atoms in there, hydrogens, a nonmetal, and oxygens. These have really long, or really, really short names, where these oxyacids, the rule is if there's an 8 on the ion, you just replace it with ic acid. But if it's ite, the anion has an ite ending, then you end it with us acid. So HNO3, that comes from nitrate. The nitrate is attached to it. So the name of this acid is nitric acid, and that's it. What anion is that? Phosphate. It's phosphate. So I want you to identify the acid first. So that's phosphate. So then what is the acid name? Okay, so phosphoric acid. So 8s become ic acids. Okay, HSO4. What's SO4? 2 minus. Sulfate. So then what would the name of that be? Sulfuric acid. Okay, and then the last one, SO4 is sulfate, so SO3 is sulfite. So instead of sulfuric acid, this is actually going to be sulfurous acid. So these acid namings is really, it comes together if you're really well prepared with the anion names. Because if you know the anion names, just applying the different ending rules is not so bad. All right? Okay. There are acid namings. Okay, so let's talk about simple organic molecules, and we'll blow some stuff up. Okay, so simple organic molecules. So we get a lot more complex than just 2 elements in like a binary compound, like carbon dioxide or carbon monoxide. Things can get more complicated. And one of those things can be in the form of a alkane or a hydrocarbon. Remember, organic chemistry is this huge branch of chemistry that takes many, many semesters to complete. And so hydrocarbons are just molecules that are made of carbons and hydrogen atoms. Okay, hydrocarbons. So when we have carbons in a chain, there are hydrogen atoms attached. And so the rule is carbon always will form 4 bonds total. And so if you know how many carbons you have in a chain, you can connect the correct number of hydrogen atoms to ensure that there's always 4 bonds, so you can figure out what the formula is for any hydrocarbon. Right? So what I want you to know are these prefixes. I want you to know that methane, means 1 carbon. Eth means 2. Prop means 3. And so when we add the ane ending, that just means we add enough hydrogens so all those carbon atoms have 4 bonds. So if you look at any one of these carbons in these molecules, there's always 4 bonds to that carbon atom. All right? So if this is methane, ethane, propane, what is 4 carbons in a row? C4, or sorry, the name of it. So this would be butane. Okay, because 4 atoms is bute. All right, 5 atoms? Pentane, or 4 carbons, I'm sorry, pentane, right? So I need you to know the name and the formula. And you might be thinking, Dr. N, there's so many on there, how am I going to memorize them? Well, simply, if you just draw the structure, you can count how many hydrogen atoms that have to be there, all right? So if I could tell you, like you do not have to memorize these, okay? If I wanted to draw butane, I would just take 4 carbons in a row, right? I would ask myself, this carbon needs how many more bonds? 3. So 1, 2, 3. Those are all hydrogens. The next carbon needs 2. Next one, 2. Next one, 3. So then I just count. Oh, this is C4H, how many? 10, right? And so you might be thinking, oh, Dr. N, I'll just use the equation 2N plus 2. That only works for one situation, saturated hydrocarbon. So let's look at this one. What about ethylene? 2 carbons double bonded to one another. This carbon already has 2 bonds. So how many more hydrogens do you need to draw there? Not 3. It already has 2 bonds. Carbon only wants 4. So you just need 2 hydrogens on it. And then the other carbon also needs 2. So this molecule, ethene or ethylene gas, like what we put in torches often, this is C2H4, all right? So does your precious 2N plus 2 trick work here? No, it doesn't. So don't do it. Just draw the structure and complete it so all the carbon atoms have 4 bonds to it, all right? All right, so let's look at line structures too, okay? Because I can tell you that writing all those carbons and hydrogens can be a nuisance. So we can also use line structures which represent carbon atoms where any 2 lines have a joint or an end. So for example, this is octanol. Oct means how many carbons? 8, yes, so let's count them. There's a carbon atom here, and here, 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 here. This structure, a lot nicer to look at than all of those C's in a row. Are there 8 carbons there? There should be 1, 2, 3, 4, 5, 6, 7. Yeah, there's 8. Yeah, there's 8. Okay, but what's not drawn? All the hydrogens, because right now it looks like those carbons don't have enough bonds. But here's how we just clean it up, okay? We always know that carbon needs to have 4 bonds. So we can just ignore the hydrogens, but still understand that they're there, all right? So if we go through this first carbon atom has 1 bond to another carbon already, so how many hydrogens are attached to this carbon? 3. 1, 2, 3. Perfect. What about this carbon? It's going to have how many hydrogens on it? 1, the next one, 2, next one, 2, 2, 2, 2, and then the last one, 3. And that's how we determine how many carbons and hydrogens are on there. So we can ignore this OH bond. This is what makes it an alcohol. All right, that OH group is already completed, but it does count as one of the bonds on that hydrogen. So let's go through this. How many carbons are on the structure? 8. How many hydrogens? So count 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17. Did I miss one? The one right there. So there are 18 hydrogens. And then how many oxygens? Just one. Just one. So this formula is C8H18O, or you can make it look nicer. You can say CH17OH, where the OH implies that this is an alcohol group, because that OH group makes it an alcohol. I can guarantee you there will be a question like this on the exam, where I give you a line structure and you have to tell me the formula. And I promise you, you're precious, 2n plus 2 rule will not work. If you have no idea what I'm talking about, then good, just ignore what I'm saying. Okay, perfect. All right, so this is the last slide. I just wanted to show you, we talked about alkanes, so all carbons and hydrogens, but there's, again, I mentioned that organic chemistry is this beautifully large topic where they look at a lot of different functional groups or groups of atoms. We have alkenes, alkynes, amines, carboxylic acids, all these things with different reactivities. Do not memorize these. I just want to show you the wealth of information of organic molecules. You might see words like paraffin, olefin. Those might be words you're used to hearing. What that means, paraffin means hydrocarbon that's saturated. Olefin means double bonds. And so if we look at the different forms of ethane, eth means how many carbons? 2. Ethane has 2 carbons. Ethene has 2 carbons, but the bonding's a little bit different here. Ethyne, 2 carbons, but it's a triple bond. Ethanol, does it have 2 carbons? Yes, it does. Okay. Ethamine, 2 carbons, but we have a nitrogen. Ethanal, or formaldehyde, also 2 carbons. So we see this common, scientists, we try to use this repeating idea of those prefixes. Eth means 2, but we can functionalize all of this chemistry on these molecules to get the different properties that we want. Okay, so we have 6 minutes, so we'll just end at chapter 2. So that means all of chapter 2 homework is due on Monday. And so I'll use these last 4 minutes to blow some stuff up, but also introduce the group project. Oh wait, when's class over? Oh, it's at 40? Okay, then I'll definitely be able to blow stuff up, yeah. Okay, so the group project, it's live right now, so the assignment is live, and you should get an email from me at 3:40 p.m. An email to send you the link to the assignment and instructions on how to upload it. I'm asking you when you're ready to upload the assignment and your group work to reply to that email that I just sent, because it's going to expedite and consolidate all of the assignments and submissions in one place for me. So I'd really appreciate it. When you're ready to submit your group work, just email me back the email that I sent to you in 10 minutes, okay? And so I have instructions there on how to do it. So this is the assignment I wanted to show you. It's due next Friday at midnight. It's submitted electronically via email. If you are aware of how, math, calculus does written homework or physics group projects, it's kind of like that, but I think mine's easier, where you can have up to 3 group members. You can choose, I don't care if you're in the same lab section, anyone in Chemistry 1220, but only 3. You can choose your own groups. You don't have to group if you want to, but I highly encourage you to. There's a submission instructions. You have to email it to me, and all of the group members need to be CC'd on the email. So one person sends it, but CC's everybody with the PDF to it. This is how I can expedite getting feedback back to you, because if I have an email that I can reply with everyone's email, I can send the grades and the feedback quickly. So if you send it to me crappily, then you won't be getting fast responses or fast feedback back. All right, so those are the submission instructions. Do include everyone's name on there. All right, so what is this? I have a grading rubric where I will look at your written answers and look at citations that you may post, the professionalism of the answer that you give me. Do you include units? Do you consider everything that's proposed in the question? And finally, do you give a reasonable solution? So the idea behind this group project is if you're working for industry, your boss gave you a question of, solve some type of problem. Can you come up with a reasonable solution that you could present like in a group meeting where it's professional, all of the work is there, your colleagues can follow you. But this is something where I want all of you to discuss with one another what the answer could be because one, I wrote this question, so you won't find it anywhere because I wrote it. But the idea is there's not any one answer, right? I'm looking for like a magnitude in an answer, all right? But what I am looking for is professional writing, clear writing. Can we use scientific language, show units, use the concepts that we learned in class up until now to answer this question? So work up to with 3 people. I want you to discuss all of the considerations of this question. I will not help you on this. I want you to discuss it with your peers. You are encouraged to look things up. You're going to have to look things up, but do cite them. Yeah, it's due next Friday. All right. Okay. Any questions about this? So it's already posted. You can get it. Oh yeah, I was going to blow up the balloon. You want to blow up the balloon? Okay. So we'll celebrate our finished second week. Chapters 3 and 4 we have to finish in the next 2 weeks before our midterm. All right. So they accidentally they made a balloon, but some of the gas escaped from it, leaked out. We're going to be learning about chemical reactions here soon, and we'll learn here is that the more stuff that you react, typically the more product that you get. So in which balloon is there more reactants present? The blue one. So if heat and boom are our products, which one's going to go boom more? The blue one, yeah. So let's test that theory out that this balloon is not going to produce as much of a reaction as this balloon. So let's see. These ones are very loud because last time I forgot to ask for oxygen gas in it. Oh crap, they didn't give me a lighter. Does anyone have a lighter? Come on. Someone have a lighter. Or I can't do this. I can't do it. No one. No one? I guess I can use this. I don't want to. It takes me a long time to light. Dang it. Okay. All right, so let's try this again because no one has a lighter. I can't believe a room of 250 people, no one has a lighter. Okay, everyone has to do ears. This is louder. I'm going to do the purple one first. I don't know. I don't know if it's going to be loud. I don't know. Okay. All right. Yeah, so okay, you have to do your ears. Like, I'm serious. This one, that was loud. What about this one? Okay. So let's see this chemical reaction. All right. Celebrate our second week of surviving chemistry. Jeez. Don't clap. Don't clap. I'm disappointed. No one had a lighter. Okay, all right, you're excused, I guess. Go talk about chemistry.